Yeah, thank you to the organisers for inviting me. So I kind of have two hats. I have one at the University of Oxford. I have a chair in biostatistics. That's a joint position between the medical school and the computational statistics and machine learning group in the Department of Statistics. And I'm also a scientific director for health at the Alan Turing Institute, which is just down the road here. And I would say, and it's a genuine call out, if you want to come and have a look around, you know, it's a really interesting space. It's the National Institute for Data Science and Machine Learning. We have we're in the British Library. It's a really nice office space. We have about 300 researchers, or space for kind of 300 researchers, all working on the kind of methodology and theoretical side of machine learning and data science. And my interest here, and reflected in this talk, I'm really interested in this interface of kind of statistical machine learning and applications for health, hence why I'm here. And so in my talk I said I was going to talk about Bayesian fitting and model evaluation, and I'm actually not going to have the time to talk about the evaluation side, although I think that's interesting in its own right. But so I'll mainly focus on fitting Bayesian models in the context of a robustness argument that says, well, you don't believe you actually have the true model. Yeah, so, and of course we never have the true model. So I'll talk about some recent results that we've been working on. Some of it's a bit quite theoretical, but hopefully give you some insight into the methodological implications of that. So I'm very interested in working in Bayesian models in high-dimensional spaces involving different data modalities, which I think are kind of challenging from a foundational perspective for Bayesian inference, because Bayesian inference assumes you somehow have captured the true sampling distribution. I'm going to talk about uncertainty quantification for parameter values, and this kind of, I wouldn't say kind of new approach, but this approach where we're using Bayesian nonparametric models to train parametric models. So if you think about, take a generalized linear model, logistic regression. So rather than fitting that using a conventional Bayesian approach, using WinBugs or something, what I'm going to do is I'm going to take first of all, kind of train a non-parametric model to then train the parametric model. And I'm going to try and convince you that that's not a ridiculous thing to do. And I'll have some examples, a small example at the end from taken out of a genome-wide association study, actually a focus region of a genome-wide association study. So a little bit of kind of Bayes 101. So Bayesian statistics is kind of founded in decision theory, and optimal decision making under uncertainty, principally following the work of Savage. And Bayesian statistics essentially uses probability as a vehicle. I think it's a really important thing that sometimes there's a confusion about what's random or what's not. To Bayesian, that doesn't matter. There doesn't have to be a notion of a kind of true stochasticity to something for you to use probability. So we're using probability just as a vehicle. Yeah, and we're just using it as a vehicle to express degrees of belief in something that we don't know about. And then we're going to use probability calculus, Bayes' rule, to update that. And the nice thing about that, as shown by Savage, is that if you take this approach of using probability as a vehicle to express uncertainty and updating using Bayes' rule, then you obtain all sorts of coherency that you might not do if you just tried to do it in a different manner. And it also, Bayesian statistics allows us to apply probabilistic modeling to a wider class of problems than would be done using non-Bayesian approaches. For a teaching example is the number of coins in my pocket now. That's not really a random variable in any sense, but from a Bayesian perspective, it doesn't matter. Yeah, all that matters is that you have a state of uncertainty in the number of coins in my pocket, and you will use probability to express that uncertainty. Use probability as a vehicle. And then if I gave you some information, you would then use probability calculus and Bayes' rule to update your beliefs. So I think that's a kind of an important distinction between, there's not a kind of notion of randomness there, we're just using probability as a tool for information propagation. Okay, and at the heart, of course, of Bayesian inference, the way it gets its name, although you don't actually have to do this, but at the heart of Bayesian inference is Bayes' rule or Bayes updating, that says that the posterior distribution, your beliefs about some unknown theta that you care about, having gathered some information, are proportional to the prior beliefs times the likelihood. And so that's that kind of prescriptive updating rule. It's prescriptive. It says that if you have prior beliefs and you have some data and a likelihood function, you must update in this format. Otherwise, you could be led to states of incoherence, which would mean that if this side of the room has the same prior beliefs as this side of the room on some unknown quantity of interest, and I started feeding you data one at a time. I've got n observations, I feed you one at a time and you're updating, and this side I give you all of the data in one block, and you update in one block. Now for coherency, you would want for you to agree. It would, you've got the same information, you had the same prior, and if you wish to remain coherent in any decision making that you would then address, you have to use this. That's the prescriptive nature, the axiomatic nature of Bayesian updating, as in Savage. Okay. So in Bayesian statistics, that likelihood function actually has another special, it's called the likelihood, but it's a bit more specific. It's actually a sampling distribution, which means it has to be normalized. Yeah, so it's actually, so the likelihood function doesn't necessarily have to be normalized, but the sampling distribution in the Bayesian model does, and it represents the joint probability of generating the data that was observed. And it's written, as a function of the thing you care about, the theta. So for example, if observations are discrete, then the likelihood assigned to a parameter theta is just the probability of generating the observed data from the model, given that value of theta. Okay, so formally that, like you said, what's the probability if I was to generate data over and over again from this likelihood function with this value of theta, that it would exactly match the observation? And just as an aside, it's this constructive argument that underlies things like approximate Bayesian computation, which is a kind of a new approach to working in challenging model spaces. However, and this is a kind of part of my interest in a bit more towards the kind of foundations, is of course, well, not of course, first of all, the statement that really resonated with me since I first studied Bayesian statistics is all of Bayesian statistics is model-based. Yeah, and that's not true of non-Bayesian. Everything that you wish to do in Bayesian statistics involves building models. Yeah, so if you were testing, so in non-Bayesian statistics, if you were testing or doing variable selection or doing inference, you might adopt different approaches, whereas in a Bayesian framework you don't. You build joint probability models. Yeah, and of course the flip side of that, though, is we know all models are wrong. And so if all models are wrong and all of Bayesian statistics is model-based, where does that leave us in trying to interpret this object? So kind of formally, this object is the posterior distribution. You've run a Bayesian analysis, you've run it in WinBugs, it's kicked you out a characterization of the posterior distribution. What actually, what is that object that's coming out from my analysis? How should you interpret probability statements? And I've had people, including referees actually, on some early papers say, well, just, why are you doing this? Just keep calm, kind of carry on, kind of thing. So, but if you do, if the model's wrong, and I take decisions using that posterior, well, first of all, what does it represent? And secondly, can I trust this object to plug into a decision analysis? Yeah, now, of course, careful model checking, model validation kind of alleviates a lot of those concerns. So you wouldn't say, well, we all know we don't ever really capture the true likelihood function. So we would want to do careful posterior analysis, checking residuals, looking for perhaps structures, transformations of variables to look at that. But I was, it's still kind of, I think, interesting to address this issue of the model misspecification, inherent model misspecification. So I guess to emphasize this, that mathematically we'd write it at this, is that if you can entertain that nature here is f naught, so nature is giving you samples, yeah, so nature's providing you samples out of f naught, which is the true sampling distribution. But you're using a sampling distribution, a likelihood function f theta, a model. Yeah, and this just says that for no value of theta does that match nature. Yeah. So formally Bayesian statistics assumes that nature's true data generating mechanism is contained under the support of the prior. That's why the prior integrates to 1. Yeah. You put, of course, 0 measure outside of the support of your prior, i.e. with probability 1, nature is in the model class. Okay. So, but increasingly that's kind of being challenged, especially in the world of data science and modern applications. How can I start to think about a true generative model, probabilistic description, especially when we're trying to combine different data modalities? So, people working on UK Biobank might be, taking 500,000 genomes or genotype data on 500,000 individuals, trying to combine that with 100,000 of those who've got imaging. It's increasingly challenging to think that you could actually, do that in an accurate manner. But, as I said, models are just simply models, of course. And they're used to kind of distill salient features. That's why we do modeling, so we can focus in on the salient features of the problem to allow us to kind of make good decisions. But, formally Bayesian statements are predicated on the model space carrying truth. Okay, so where does that leave us? So what happens when you fit a false model to data? So consider one notion of a best fitted model. So here I've got a likelihood function f theta, and I'm just going to maximize it. So you could translate this equation here into, I've called GLM. Let's take a generalized linear model, take a logistic likelihood function, and let's say I've just called GLM on some data, and it's given me the estimate of the parameter, the maximum likelihood estimate. So the argmax just means find the value of theta that maximizes that score, yeah, i.e. the MLE. Okay, and in that sense you can just think of this object here, the log likelihood function, is just a score. It's just a kind of scoring mechanism or a scoring rule. And then it's perfectly valid to consider the properties of running a GLM model on data outside of the fact that the data might not really come from a Poisson distribution or really come from Bernoulli with logistic probability. Yeah. And once we do that, we can then start to think about, well, what happens, what happens to the output, or what's happening to the output of that model, as you get more and more data. So let's have a quick kind of divergence into asymptotics. Well, there's no real asymptotics here. Yeah? But it says, what would happen? So think about it. I've got my GLM model in R. I send it in my 100 data points. Suppose you had 200, 300, 400, a billion, a trillion. The output's going to move somewhere. Where's it moving to? Yeah, so what's the output of say a GLM trained with an infinite sample size? And it turns out to look like this. Yeah. So what it says is that the output from your GLM will be the thing that maximizes this expected log likelihood. Yeah. So f naught, remember I said that's nature. Yeah. So that's unknown and never known. Yeah, for data arriving out of f naught of x. And moreover, your Bayesian model is going to head there too. Doesn't matter at this point. If I give you an infinite sample size, the prior, unless it's, if it has reasonable support, over the data, that's going to get washed out. Yeah. So the prior is going to get washed out, and your Bayesian posterior is just going to head to a spike. Yeah. And it's going to head to a spike at this point. So both the Bayesian and non-Bayesian models are heading towards theta naught. And perhaps an easier way of thinking about that is in the following case, that I've got xi, these are the observations that nature's given me, and it's going to give me an infinite number of observations, and I'm just going to call GLM in R with an infinite number of observations. And this is actually kind of an interesting point in the model space. So you can see, if you look at it for a little bit of time, that value, the place you're heading to, actually minimizes the Kullback-Leibler divergence between your model f theta and nature's f naught. So you're not heading arbitrarily out. You're heading to a well-defined point in model space. Yeah, and that's irrespective of whether the model's true or not. Yeah, if the model's true, the Kullback-Leibler divergence will be 0. Yeah, because you'll head to the true sampling distribution. But if it's not, you'll head to the point in the model space that's closest to nature's f naught that's outside the model space. And that's been well known since White's paper on the robustness of maximum likelihood estimation. Okay. And so we've kind of solved one, thinking about it this way, we've actually solved one of the initial problems, which is, now if you're going to put a prior, so if you suppose you're all good Bayesians, you're sitting down eliciting subjective priors, whereas within conventional Bayesian update, you'd be kind of forced to think about the true value of theta. Now here we're just going to conceptualize thinking about where this value is. Yeah, so now your prior is about, where would this GLM model end up given an infinite data? And that's what I'm going to mean is captured in p theta now. Yeah, so it's going to be the prior on where is this value of this kind of, in some sense, optimal value theta naught. Okay. So it's where's the posterior going to converge to as I give it more and more data. Okay. What do I say? Okay. Of course, we don't have an infinite data. Yeah? So we have finite data, n data points. And so what I would like to know is, given the output of my GLM on a finite data point, can I update my beliefs? It feels like there should be a belief update about theta naught. Yeah? So given what I've currently got as an output from the maximum likelihood estimate, can I say anything now about where theta naught may or may not be? Remember, the prior was specified about that position, where in the model space will take me closest in KL. So, is there a posterior update? Now, you could just simply do that using Bayesian updating. You could say, well, I've got my prior, I'm just going to put it through the likelihood function. But as I said before, that makes a kind of an assumption that the data is really coming from the likelihood for some value of theta. And what we've been looking at is, how can you provide an update, a Bayesian update, in the absence of that? So thinking that actually, in the absence of the sampling distribution being true. And the high level view is that, if I think about this theta naught as the sense of the output under an infinite sample size, the posterior uncertainty in theta flows directly from uncertainty in nature's f naught. Yeah, if you knew the sampling, if I knew what f naught was, nature's f naught, I could just generate an infinite sample, fit my GLM, and I'd be done. Yeah, so the uncertainty in the model comes from an uncertainty in a wider sense from f naught, from nature's f naught. And so if you think about it that way, if you're committed to using this model, and the uncertainty in the sense in the optimal value flows from uncertainty in the sampling distribution, why don't we just attack that directly? So if f naught is unknown, well, I could be Bayesian about it, yeah? Because I say, well, if I knew f naught, I'd know the value of theta. I don't know f naught, so let's just tackle that directly. And that enters into this area called Bayesian Nonparametrics. So what we're going to do is we're going to try and put a prior directly on f. Yeah, and this hints at the thing right at the beginning of the talk I said I'm going to train a non-parametric model, yeah, to train a parametric model. This is what I mean. I'm going to use a non-parametric update for f, and then use that to train my parametric model and see what happens. So we place a prior on the space of distribution functions, and then learn about theta that way. And it's the essence of Bayesian nonparametric learning. Okay. I think I've said this. So if I could generate, suppose wind bugs could give me an output on a distribution function, then I could then train my model against this. Because if you give me a sample now of the distribution function, there's no uncertainty in theta. So if you imagine if you were using something like Gibbs sampling where you say draw f, draw a sample for theta, draw f, draw. There's no, the posterior for theta given f is a Dirac. There's no uncertainty. So that's just going to be a maximization step rather than the sampling. Because I said if I draw fi from the posterior on the space of distribution functions, then I know precisely how to sample. Well, there's no sampling variation in theta I. Okay, and repeating this operation would then give me a bag of Monte Carlo samples of the thetas that characterize the marginal posterior distribution that flows from the uncertainty in f. And it turns out that there's a really interesting and useful class of non-parametric models in the Bayesian literature called Dirichlet processes, which are very amenable to this problem. And for technical reasons, and I can know at least one or two people in the audience who are going to know why, we're going to take something called a degenerate Dirichlet process. And the reason why we're going to take a degenerate Dirichlet process is it's going to put all of its support on the observed data. So think about an empirical likelihood function. It puts the support on the data. We're going to get something a little bit similar to that. So we're going to take a degenerate Dirichlet process, which is going to put all of its support on the observed data. And the reason for that is going to give us a really simple update, a surprisingly simple update for this problem that we've just characterized. Okay, because if I draw this f from something called the Bayesian bootstrap, which goes back to Rubin, yeah, again, this is very similar to kind of bootstrapping if you're a non-Bayesian, yeah. If I draw an f from this Dirichlet process, what happens is that this object that minimizes this KL under an infinite sample size of this f just turns out to be a weighted log likelihood, yeah, weighted maximum log likelihood. So the MLE would have weights 1, yeah. This sample has a weights, and moreover, those weights have a very particular form. There's something called Dirichlet 111. So the Dirichlet is 111, ones, is a uniform distribution on the simplex. What does that mean? It means that they have to sum to 1, the weights sum to 1, and then they're uniformly distributed. So any point in the space of positive weights that sum to 1 has equal measure, or any region. So it's a kind of a flat prior over the simplex, over the uniform simplex. But if you look at this is now looking really nice, because what this says here, in order to do that kind of bit of the fancy maths things I was talking about before, all you need to do is draw these stochastic weights and maximize a weighted log likelihood. And moreover, this is a Monte Carlo draw. It's not a Markov chain Monte Carlo draw. There's no serial dependence. I can draw these f's independently in parallel. Yeah? So what does this say? It says if I want to do this kind of strange thing of fitting my Bayesian generalized linear model using non-parametrics, I'd say to you, well, how many samples do you want? You'd say, I don't know, 10,000. I'd say, right, just draw me 10,000 stochastic weight sets in parallel and push those into your GLM function, maximize this weighted log likelihood, not the, yeah, and then kick those out and you're done. Yeah? And what I need to persuade you is that the things that this kicks out are useful. Yeah? It's not just kind of, yeah, it has to have this particular form. Yeah? So this is just a simply a weighted maximum likelihood estimate with random weights. And if we repeatedly redraw the weights, we end up with a bag of samples from this case. Okay. This is actually, this procedure, again for people in the audience, some will already know, was originally specified in a paper, RSSB red paper, by Newton and Raftery in 1984. So everything I've said to you so far has already been done. Yeah, so, you know, you might think, why on earth, you know, does that mean it's no good? You know, it was a red paper, why didn't people pick it up? And I think there were two reasons. First of all, this thing on the left-hand side is actually not necessarily a good approximation to your original Bayesian model. And I can characterize that. Yeah? But that original Bayesian model assumed the model was true. So when people looked at this paper, they said, well, you know, I've got my true Bayesian model. If I look at this object here, does it match? And they said, no, it doesn't, you know, it doesn't really get the same kind of coverage. So we don't like it, yeah, or it wasn't picked up on. And the other thing you have to remember that it was just as MCMC was kicking off. So this big push into Markov chain Monte Carlo. Yeah, and sample sizes were relatively small to the things that we're dealing with now. So there wasn't so much of an issue in terms of runtime and convergence and burn-in for the MCMC. Yeah. But it turns out, and this is, I guess, part of the work that we've done, is that if you're any way outside of the model space, so if the model isn't exactly true, yeah, if the model's precisely true, do Bayesian inference, do standard Bayesian updating. If there's any sort of model misspecification, this object on the left-hand side is much better than the original, much better than, sorry, I'm getting over, has certain properties which the original Bayesian approach wouldn't have. So it turns out that those bag of samples from maximizing this weighted log likelihood have particular interest in objects. And I'm not going to bore you with the asymptotics here, but essentially, some of you might have heard about this kind of sandwich covariance matrix estimation, is that because we're using a bootstrap, the posterior coverage of this Bayesian model used in this maximization obtains the right frequentist kind of risk. Whereas with Bayesian models, you've got no guarantees. And perhaps the simplest example to this is to think about a Poisson regression. So suppose you're fitting, or even just fitting a Poisson distribution. Suppose you're fitting a Poisson distribution as a Bayesian, and the model was actually over-dispersed. Yeah, so there actually the data's got less information than you think it has. And what's going to happen is your posterior interval is going to be too tight. Yeah, your model's misspecified and you think you've got more information than you actually have. And vice versa, if it's from an under-dispersed Poisson, you've got more information in the data than you actually think. So there your credible intervals are going to be too wide. Yeah, now you don't, I mean, again, careful model checking and calibration. Yeah, but this bootstrapping approach kind of automatically corrects that. So you get the kind of correct, in some sense, a correct learning rate outside of the model specification. And I guess the other interesting thing is that predictively it dominates. In a way, if you define predictive risk in terms of like a Kullback-Leibler, an information measure of the risk prediction when you make it, then by doing this bootstrapping, you get better, lower risk in your predictions. Okay, but so far that's the other reason it wasn't like people said there's nothing Bayesian about it. Yeah, so it's really interesting. Even if you want to know something about people know the RSSB red papers are notoriously They invite you to give a paper and then people attack it. I think that's the kind of tradition, but it's worth reading. And of course, you know, people looked at this thing and they said, well, there's no prior. Yeah, so how can this be a Bayesian model? So that, and that's in a sense as well why it's a really, that in its form is a bad kind of, it's well, not necessarily a good approximation to a Bayesian model. And so we would like to incorporate, if we're Bayesians, we'd like to incorporate prior information. And the simple approach that we're going to use is use synthetic data. And we use synthetic data in the following manner. If you have a prior on theta, because you're Bayesian, your likelihood is a sampling distribution. It's a full sampling distribution. I can just play the following game. I'm going to draw a theta from your prior. Yeah, I'm going to draw a synthetic data set of size t from the sampling distribution, from the likelihood function. And I'm going to then concatenate it. I'm going to add my synthetic data. I'm going to now have an additional training set, which I'm just going to combine with my observed. Yeah, and so then I've got a data set generated under the prior and my actual observation. And again, I'm going to draw stochastic weights, and I'm going to do this maximization trick. And we're going to have a weight in here, a C, in front of the synthetic data, which is akin to a prior sample size. So if you set C to be n, then it's like saying, you know, I've got just as much as information in my prior as I have in my real data. You know, if you wanted to do kind of a unit information prior, would put this as 1. Yeah. And then you just randomize the weights. The weights are drawn Dirichlet, and then you maximize independently in parallel. So this is what the kind of algorithm would look like. I've said all of this, so I don't need to go over it again. Do these B draws, but again, those B draws can be done in parallel. Draw synthetic data, add it onto my real data, draw a set of stochastic weights, maximize, and then return the samples. And here's it showing what this does on a simple linear model. So, and thanks to my PhD student for doing this. I would have no idea. I was saying, Edwin, go and just do us you know, a movie of this. It should be okay. So here I'm just fitting a simple linear model, and what am I showing? Here's the data up in there. So the points are data points. Yeah, the MLE is the line that doesn't move. Yeah, I'm fitting this model on the top right, and then here are the stochastic weights. Yeah, that are kind of moving up. If you're doing bootstrapping, yeah, the kind of conventional bootstrap, these weights would be like steps of 1 over n. Yeah, and about a third of the points would have weight 0. Yeah, but here we've got it's like a continuous bootstrap. So here we've got the random weights, and you can see if of course we know linear regression, the leverage are in the points at the end. So the best thing is to wait, and if you see a big weight there, you should see it starting to track down onto this point and equally. And this is the posterior output from a pretty small run, but the thing to show is this point here, yeah, because it's an independent maximization, it just jumps around. Yeah? And the other thing this simulation isn't really capturing is that this looks like MCMC, but it's not. We just do it in parallel. So if you give me, you know, P cores, I can deliver P samples in 1 iteration. So it's trivially parallelizable under that. And you get the usual things. You get posterior credible intervals, joint distributions on your parameters. Okay. So I've said that, it's trivially parallelizable. It's also, because you're doing these independent maximizations from random starting points, say, it's good at capturing multimodal posteriors. And so again, this is just a kind of toy example with something called a mixture model, Gaussian mixture model. And that's known to be a kind of a bit of a beast for MCMC, because it's often used because we've got known symmetries. We've got label switching in the parameter space. I can pick up these parameters, I can switch them over, you've got exactly the same model. Yeah, so the likelihood's unidentifiable. Yeah, and that means that if your MCMC is running properly, you should see all of these posterior modes. But because we're doing these random restarts, you just capture them. So here's the output from this kind of weighted likelihood bootstrap. What you're seeing is you're looking at the uncertainty in centering of these Gaussian mixtures, and it just picks up all of the modes, and then this is an output from the no U-turn sampler. So these are kind of Gibbs samplers that are run, and in a sense, as expected, because you're doing a serial update conditional on where you currently are, it finds it much more kind of challenging to kind of move around the space. How much time? Am I out of time?
I think you're close to, you should be finished in 5 minutes.
5 minutes, okay. So here's the genetic association example. So we wanted to do sparse logistic regression. So there's the likelihood function, and the prior that we're going to use, and which goes into the loss, it's a student, it's actually a generalized student, but it's something akin to a student distribution. So here's the penalty on the coefficients in the logistic regression model, and you've got a scaling parameter C that kind of says how much do you want to squeeze those parameters towards 0 and how much do you want to give them kind of free rein. And the interesting thing in genetics is you get really high correlation structure that comes around because of recombination. So recombination breaks down genomes very slowly over generations, about 1 recombination per chromosome per generation. So you are mosaics of your grandpaternal and grandmaternal genomes, but big blocks. So your chromosome 1 will be split in half from your mother's side and from your father's. So what that means is over the times you still see in like European well, in all populations, these recombination blocks. So you can think about this as the kind of variance covariance matrix. So it's really blocky, and that normally means that you have trouble. But because again we can do these random restarts, this looks like a lasso type plot, but these are kind of credible intervals. And what they show is that if you start relaxing the penalty, you get more and more kind of variables into the model. And what I've shown here is the lines are the medians, yeah, of the posterior. And when you first look at this, you go, hold on a second, something's a bit weird here, because you're getting really kind of a lot of jiggle in the median. But if you zoom in on that, you can see exactly why in the next plot. So this is now a kind of this is now looking down on that parameter as a function of the amount of shrinkage, and it's because it's bimodal, yeah? So you either kind of said, well, it shouldn't be in the model, or it should. And again, you kind of, you capture that with that. So this is just from the posterior output. So this is my final slide. Traditional Bayesian approaches formally assume that the sampling distribution is contained within the truth. This non-parametric approach doesn't. It's important to note that the non-parametric approach wouldn't give you the same as the parametric kind of conventional Bayesian. They're targeting the same parameters. They're both learning about exactly the same parameter. So whether you like it or not, the Bayesian, we're both heading in the same direction as you gather more data, but they're conditioning on different states of knowledge. So this right-hand side is conditioning on the true data generating mechanism being within the model space. And just to note that it's scalable, because for IID likelihoods, you can just parallelize it. And thank you. And if you wanted to learn more, we've got a paper in the kind of Statsy journals, but then also one in like the NIPS and just recently in ICML. Thank you.